Okay, so the website is Epigenome gateway.uso.edu. You can also go to, I believe, epigenomegateway.org. So that's a cloud instance. Okay, so now you're at the main browser website. Let me see if I can't make it smaller. Sorry, just because of this Zoom, we are, oh, come on, go away. All right, we'll just, okay, so a little bit better. So this is our main website, okay? Just quickly, a few things. At the very top, this is what we call the legacy browser. I think this is the browser, Jen, you've been using. If you click this, you can actually go to the old browser. So this is, oh my God. This is the old version of the browser, okay? So this is the legacy browser. As I said, I've run this workshop, 20 times, but all on the old browser. Today is the first time I run this on the new browser. And I think this goes to the developers page, right? This actually, I'm going to start a new page here. This is the support page. Come on, go away. Go away. Huh? Oh, okay. Oh, okay. This is the support page, right? These are the tutorial books. The first line here is what we just recently updated. If you click on this, you're going to get a PDF. Oh, sorry. This is actually today's, script, right? So this is not the booklet. This is the tutorial for today. This is a tutorial book, right? So this is today's workshop. So if you go down here, this is today's workshop. If you click on this, you get to a web page, right? Describing the workshop. There are two PDFs here. The first one, let's see, if you click, this is actually the booklet. Again, I didn't bring too many. I brought 30 copies, but you can get a version, online version here. So this basically introduces most of the features of the browser, right? It's about 30 pages. Okay, so most of the functions. So it's a handbook, but you actually learn to use the browser by just playing around it, right? So, but this is a good handbook to have. So I'm gonna close this. The second PDF is a PDF for today, right? So this describes everything I'm going to demo. I probably won't remember all of them, so I printed out the versions. I'm going to go through this with you. I'm probably going to skip some. I'm probably going to forget some, but this is what I prepared to do for today. So if, for example, you become sleepy, you can always come back to this, later. Or maybe you read this, you become more sleepy. Right? But this is basically what I prepared for the 3-hour workshop. And there's lots of stuff there, right? So 25 pages, but all the details are there with screenshots, so you will know where you are. So I'm actually going to keep this page here just in case I need to use it. I have a couple of things here that may be useful. One is a JSON file. I'll explain that later. The other is just a bunch of coordinates. I'll explain that later. And below are some of the links to previous workshops. If anyone's interested, you're certainly welcome to check out what we run in the past. Okay, so that's the support page. Okay, so now let's go to the browser. And we're gonna click this link, explore the new browser. We're gonna get to the actual browser site. I actually need to, let me actually clean, let me try this. How do I exit? Yeah, I want to restart Command Q. Hold. Oops. Oops. Where was I? Okay, let me do this again. Just get a clean. Okay. Okay. So let's just slow down, right? So I click on this. I'm going to launch the browser. Now I have the choice of choosing different assemblies. Right? So at this point, I have 5 species there. This is something that we're going to talk a little bit later. We can upload a saved session. I'll talk about that a little bit later. The old browser actually support at this point 15, so I haven't migrated everything over. So now we have 5 species here. Click on human, you have 2 choices, HG19 and HG38. Right? So most of the data at this point are still at HG19. So I'm going to click on this and go. So this launches the browser. So at this point, there's no data yet. We're going to get data very quickly. But just very quickly, it's very colorful somehow. I just like color, right? You have to spend some time to get familiar with the interface, but it's loaded with function. If you look through, this is where you can change. This is human HG19. This is genomic coordinates. This is the menu that allows you to control track and activities. There's a lot of applications, so these are the apps. This is where you can set and change setting. Help page, all sorts of. No, I'm good. Oh, thank you very much. In my office, I actually stand and work. I only sit down when I have meetings. So for example, here's help, right? So there's documentation. You can click and, you just click link to old browser. You can join a Google group and ask questions there. You can join our Slack channel. You can get source code. Everything's open source. For example, if you click on this, you can just join the Slack, right? So we have a workspace designated for this. We have engineers watching this all the time, so you can ask questions there, give us feedback there. Okay. Sync. This is the Slack channel. Where's the browser? No, this is real time, right? Where's our browser channel? Yeah, this is the Epigenome browser channel. Okay. Okay. So this is very typical. This is the chromosome ideogram. This little tick here represents, just tell you where we are in the genome. These are some two buttons that you're gonna, that allows you to perform different functions. Zoom in, zoom out, move around. You can click and move around, right? You can move back, right? So right now you're only seeing the gene track. So this is a HOX-A cluster. You see a gene track. Now this is already something that kind of special to us. This is our own repeat masker track, transposable elements, right? So, we actually, if you zoom in, this one, you see that we give, we actually give the names of those transposable elements there and separate them based on different classes. The height of the transposable element represents how close this particular copy is with the consensus. So this is what I mean by actually putting a lot of effort to create a new visual format, right? So better ways of express the data, right? For transposable element, that's what we our research based on. It evolves around transposable elements. So we actually come up with a lot of different ways of looking at them. So let's zoom back up. So pretty typical stuff, right? So rulers and things. So this is basically a genome. This right now we're looking at a 1.2 megabase region. Again, you can zoom in, zoom out, however you like, right? You can move around. So let's quickly add some data, but I'll come back to tell you a whole lot more about adding data. I'll just add some data to illustrate some of the functionalities. So I click on track. I click on public data hub. So here you'll see a lot of data hubs that we host. So there's actually how many? This is where you're going to get data. Data are organized a little bit differently. So they're organized based on, so these are roadmap data, these are ENCODE data, IHAC data, interaction data. So we have a lot of data here, and you can load these hubs. So right now, I'm just going to load one hub, which is roadmap data from Geo. So this data physically actually stay at Geo, right? But we just remotely accessing them. We just loaded 2,728 tracks. Okay, so I'm going to exit. So we're actually fetching the data, right? So the browser is actually fetching some data. So we have 2,000 tracks. We're not going to show all 2,000. We're fetching. I think by default here we're fetching 10 tracks, 10 data sets, 10 or 12. You probably realized earlier already, the tracks are loaded at different time. Basically you can still work on other stuff when other tracks are being loaded. So that's actually I don't think any other browsers allow you to do that. It's a sort of an engineering, software engineering thing. So we just got loaded a bunch of data. This is where you can now start to, you can move the, browser, and then they're going to refresh. And before you refresh, you can move back, right? So these are all sort of a software engineering tricks that we put in there. So we are at the mercy of the Wi-Fi here. So I don't know if the this interaction is kind of reasonable, I think. Okay, so now we added some genomic data. I'm just gonna very quickly go over this genomic data. So the first track, so on the left is the name of the track. You mouse over, it tells you it's ChIP-seq input for cell line called IMR90. Next one is a H3K4 trimethylation, this promoter mark for IMR90. So these two are promoter marks, right? I think these are replicates. And these two are K4 monomethylation, the enhancer marks, they're replicates. These two are K9 trimethylation, IMR90, same cell line, repressive marks. And these two are K27 trimethylation, also repressive marks. At the bottom here, this is actually a CRUM-HMM track. So CRUM-HMM is a software tool that integrate multiple types of histomodification and come up with states for different regions. So, this include like promoter states, enhancer states, quiescent state, and things like that. Okay. So this is very typical, right? So this is most genome browsers will allow you to display data like this, and we're no exception. So I told you that we have something that others don't have, that is the metadata, right? So now I'm going to show you how to add the metadata. So if you click on this, right, you see the terms that you can add as metadata item. So you can say, okay, I'm going to add track type, maybe sample, maybe assay. So I added 3 metadata types, and I can also define my own metadata. Right? So this is basically, annotating your data sets. Okay. So now you see, oh, I added another map on the side, and this map is sort of displaying the metadata of the genomic data. I have track type, so I have bad graph, that's the track type here. This is meso-C track, so this is something I'm going to tell you a little bit more. This is actually how we display whole genome bisulfate data. I'll tell you a little bit more there. The second one is sample, so every one is the same, it's IMR90. Third column is assay, so you'll see this is chip-seq input, this is K4 trimethylation, K27 trimethylation, this is CRUM-HMM, this is meso-C-seq or whole genome bisulfate, right? So you can actually add your hit metadata there, and then this metadata can you can define your own, right? So you can use this to group your samples. Okay, so just a few very basic sort of manipulation, right? So for example, you want to, let's see what we can do here. Let's say you want to change color. Let's say you want to change color of a particular track, right? So you right click on this, you get that highlighted in yellow, and you see, oh, there's actually a whole lot of things you can do to configure this track. You can change the track name, label, right? You can change this to, I don't know, I don't know, let's see, set. Way it changed there. Right. So when you publish your paper, it's give you some flexibility. There are different ways of displaying this data. You can display them as, by default, this is graph. This is Wiggle track, right? But you can turn that into a heat map, right? You can turn that into a heat map. So this is actually, what you can now compress and then display a lot of data. So I'll show you one example later. But typically, you want to display this as a bar. So that's automatic, by default, is a bar. Y-axis, you can So right now it's automatic. Oh, I guess we're, you can change the height of the track. You can make it taller. You can, right? You can make it, what happened there? Doesn't go down. Yeah, you can put in a number 50. Yeah, it went back. There's some response delay there. So why scale? You can do auto. Auto basically means, when you scroll, the track will maximize the usage of the space, right? So that's basically auto. But you can do fix, right? So you can say, okay, I'm gonna use say 50 as my height, right? So now this track is 50 pixel tall. Actually, earlier you see 10, right? So let's make a 20 here. So now you see the values that are greater than 20 get cut off, but we use a little bar there to represent that, right? So that's probably more easier to see if you do this, right? So you sort of cut off there. So you can do that. You can go crazy with color, right? So you can say let's come back to auto. So you can go crazy with color. So right now it's sort of make it yellow. Okay, make it yellow. It's yellow. Make it purple. It's purple. Right. So that's primary color. That's the color for positive values. I don't have negative value here, but you can also change negative value. Right. You can change background. Let's make yellow the background. Whoa, you're creating, nice looking tracks now. You can smooth your data, right? So this is raw data, but you can apply algorithm to smooth that. Right? So that's all sort of done bioinformatically, right? So people do that with, you smooth your signal, the signal does look better this way. Okay. I think earlier when we did this, you can also change the color for this. So this is right now it's red. We can change that to green. Right. So now this part becomes green. So I mean, you're not gonna remember all this, but the point is you have maximum flexibility in how you want to configure your track. I think this one also gives you more information. Like this actually tells you where the data is from, right? Some of the metadata information, right? So these are the, you right click, you get to this config page, you're gonna learn a whole lot about this data set, and you're gonna manipulate the data however you want, right? So that's one thing I can show.
I think you can also show this feature. The adjustment can be applied to all the tracks at the same time. Yeah. So you get a nice, even screenshot that's ready to be published.
Yeah. So let's say if you want to do this for let's try this. Okay. You actually, if you hold down Shift and then do your, wait, hold on. If you hold Shift, you can highlight multiple tracks. Or you can actually apply this to the entire view. But now let's say we can do this together for 4 tracks. I'm gonna make these tracks, a little bit shorter, right? So 40 is good. I'm going to fix the scale by 30. Yeah. I'm going to smooth a little bit. I'm going to change my primer color to blue, this type of blue or this type of blue. And there's all sorts of things you can do. You can design your own color. You'll change your background to, where's pink? My favorite color is pink. I have two daughters, so I have to like pink. Yeah. That's a nice color. You can go crazy with this, but okay. So what else I can do here? I'm not following my script already. Let me tell you a little bit about this Meso C track. Okay. So oh yeah, you can rearrange track. Of course, you can move them up and down wherever I'm moving this up. Right, so you can do that. You can actually, so this is the list of your tracks. You can rearrange them. You can move things around. Right? You can move things around, and you come back, and you see, whoa, my track is all rearranged. Right? You can obviously move this. By hand. Where did that track go? Oh, this is it. Okay, I'm going to say a little bit about, use this Meso C track as a example to, again, illustrate, if you think just a little bit more, you'll find more expressive way of looking at your genomic data, looking at your data. Now, Meso C, or whole genome bisulfate, is used to measure DNA methylation. Okay, so how do you want to look at DNA methylation? It's very intuitive. Okay, you have CpGs, methylation level goes from 0 to 1. So, very naturally, you think I should use little ticks to represent DNA methylation data. And in fact, that's most people do that. Go to UCSC browser, that's the kind of track you see. But that's just not enough. I'll give you one example. For example, if you have a CpG where you sequenced, you have like 50 reads covering that CpG, and every read tells you the methylation level is 0. Okay, so the methylation level of this CpG is 0. You have another CpG that you have 0 read coverage. You don't know the value of methylation for that CpG, right? On the browser, if you use that little tick, you cannot tell them apart. Right? You cannot tell apart a CpG with no value from a CpG that is methylated level, the methylation level is 0, right? So, I mean, it's not a, maybe it's not a big deal, but it is a big deal. It's like, you're not showing your real data. The data contains more information. So how do you deal with it? It's actually very simple. In our hand, it's very simple. We added a background color for CpGs with read coverage. Okay, so now, you have a background color for that CpG, and the foreground color is the methylation level. So if you only see the background color, this CpG is being interrogated. I have a sequence, over it. I have sequenced it, but the foreground is 0. That tells you the methylation level, right? So it's a very simple idea, but it actually goes a long way. So related to this, if you have a CpG methylation level is 50% based on 100 read, you're very confident about 50% because 50 read says methylated, 50 says unmethylated, so your methylation level is 50%, right? Perfect. But you can also get a 50% call based on 2 reads, right? So one read says methylated, the other says unmethylated. So it's also a 50%, but you're probably not very confident about that level, right? That information is also lost in the typical way of looking at whole genome bisulfate data. Both are 50%. You can't tell them apart, right? So what we did is, in the background, we added a line denoting the coverage, right? The read coverage, which is the confidence level. Okay, so that's what I'm going to show you here in this meso-C track. So first of all, I'm going to quickly do something called combine the track. So this is the meso-C track. I'm going to make it a little bit taller. Okay, I'm actually going to zoom in to a region where you're going to see, sort of hopefully you'll see the point here, right? So now you're in a region where the background actually tells you there is a CPG being interrogated. The foreground tells you the actual methylation level. Right? For example, in this region, right, you actually have a lot of CPGs being sequenced, but because the methylation level is low, you won't tell them apart, right? So it's unmethylated or not. You can't really visually appreciate that, right? So you can let's zoom out back a little bit, right? So, but having this background color tells you, okay, those are the CPGs that we have covered, and then the methylation level is so and so. And you can sort of, if you mouse over, you'll see, okay, this particular CPG we've sequenced 16 times, right? The methylation level is 0, right? So all 16 rates agreed that's 0, right? You get that specific location, right? Over here, you have actually a methylation level of 55%. Sequencing depth is 38, right? So again, all the information is from the same data, but by presenting the data a little bit differently, you actually learn you actually learn a little bit more, right? So you know the confidence level, the difference between no data versus 0, right? And then now you're pro. Now you can go ahead and then change the color. Let's change the CPG into red. Let's change the background into, where's the background? Yellow. Whoa, no, that's actually the background of the track background. Where's the color background? I can't even find it. Where is context color background? Oh yeah, this one. Yeah, this is the background. Thank you. It's me purple. Oh, this is too strong. Actually, we should make that yellow and change this background to green. Yeah. It's weird. But you can do whatever you want. Okay. So the other thing is you can, oops. Okay, so the other thing you can do for methylation track for this doesn't look too bad, right? I should change this background to make it a little bit light. Yeah. This is all very ad hoc. So the other thing is, by default, we actually split the 2 strand, right? So this is, you can click and split it to 2 strand, right? So most of the time they're asymmetric to each other, right? So in terms of CPG methylation, but this function comes handy when you look at non-CG methylation, right? CHG methylation, which is different between 2 strands, and then you'll be able to see that. I don't think this track will have CHG data. It's all CG, right? So basically, this is a way to just illustrate that we have we have thought a whole lot about how to present genomic data, and that data, it's the same data. It has all this information, but how do you let that information come out visually? Okay. I don't know if this is a good time to take a break. Yes, I see coffee is here, right? Okay, let's take a break. We'll come back and do a few other fancy or nerdy stuff. All right, how are we doing? Okay. Wow, this is getting prettier, huh? With all these colors. So, there are a few other things I plan to show, not in particular order. If there are questions and needs, you want to see how certain things done, please feel free to just interrupt me, okay? So, during the break, I was asked, how do I find the data of interest? Okay, so let's start from there. Let's go there, okay? So, we now know how some of the tracks behave. So now let's find more data. So click on track. There are different types of tracks, right? So there's annotation track. So these are just genome annotation, CPG island and things like that. You can click, you can see, have rulers, have gene track. So variation. Here you can see ruler, that's already added, right? Wherever you see this green button, you can add that new thing, right? So some are added. Conservation. Oh, conservation is a good thing to add. So let's add vertebrate fallopi, for example. We'll add a track, right? So this is, the annotation track. Where is it? It's being added at the very bottom. Okay. So this is a fallopi score. Lots of people use this to look at conservation. Public data hub, this is probably the most important place because all the data that you want are from there, right? So you can add from roadmap, that's where we add it. And then if you want to add encode data, just keep going down. So we have a good number of data hubs there. Later, we're gonna look at Hi-C data, chromatin interaction. We'll come back here and fetch some data. Now, the next one is this facet table. So this is how we organize tracks in the genome browser. So you can actually create this facet table yourself. At this point, it's organized by sample and assay, so rows and columns. But you can change that to other ways of organizing this. Sample, you can click on sample, you're gonna see there's a cancer, fetal, adult. Assay, you can see, their expression, epigenetic, and so on and so forth, right? So, so that's one way of getting into a specific data set. Say, for example, I'm gonna go into adult cell, I'm gonna go to blood, I'm gonna go to lymphocyte, I find this GM line, this is the encode line, right? So I can go find their data. Actually, this is roadmap, so it actually doesn't have a whole lot of encode data. There is one data set here. You click on this, you see this actually HMM for this GM cell line. You click add, right? Being added. Okay, I'm going to come back here. So this is the GM HMM. So added at the very bottom, right? So let's come back to our facet table. So this is how you can, if you know, okay, I want that particular sample, that particular mark, this is how you can get to that point, right? So find what you need. You can also do a search, okay? So what you do here is you click on, okay, so before I say, so you can see here there's two numbers. There's a 12, there's 27, 28. The 12 means the tracks that are being displayed, right? And then the 27, 28 means the available tracks. So that's the track. You have more than 2,000 tracks. That's where you're going to find your, the data that you're interested in. As I mentioned, the overall, we have like 180,000 data set, right? So you can do this by just using this faucet table to find your data of interest, but you can also do this search. You click on this. This is basically all the data that's available here. There are 137 pages. Each page you have like 20 rows, right? So you can scroll down and find your data of interest. You can also do a search here. So the search is designed such that now under name, for example, you have a box. Let's say you call, I'm going to do fetal brain. Okay, so this is basically a filter. So all the fetal brain data is now listed here, right? You can do another filter. You say, okay, I'm going to do a H3K4 ME3. You just got filtered down to 2 data sets. Right? These are actually replicates for H3K4 trimethylation for fetal brain. And now you can add them. Right? So this is how you add this 2 data set. Let's say let's add a little bit more. Let's add a K. Do I have K9 trimethylation? Oh yeah, we do. Let's add a couple. I don't know why there are 3, but we can add them all, right? So this is how you navigate through these thousands of data. You can do search. You can just follow the FAST table to get your data of interest. Now coming back, where do we add the data? Right here, down here, right at the very bottom. And you can see the way this data are added is, by default, we only use a little bit of space, and there are heat maps, right? So, and this is what this allows you to really put, hundreds of tracks together in heat map in one view, if you want, right? Now this part is now we're now pro. We can group them and then config and then change. I say, okay, let's make them taller. Right? We just made them taller. And we see, these 3 tracks look not, these K9 trimethylation, they don't look like that amazing. Let's remove them. We can remove them. Okay, so these two tracks are added here. Okay. So, so this is how you select tracks. Okay, you've done all this work. Time for coffee, time to go home, time to power off your computer. You probably want to come back to this hard work, right? So you don't remember what you did. So, next time when you come back, you can recreate this. Honestly, I won't be able to recreate this because we did everything sort of on the fly, right? So, and you want to show this to your colleague, friends, PI, your daughter, if they're interested in. So you want to keep a record. You want to save this. So that's when the session function becomes useful. Okay. So that's what I'm going to demonstrate next. So actually, yeah. So just to finish this part, right? So you've now look at you've now know how to get to the public data hub, how to navigate the facet table. This custom track is how you upload your custom track, right? So we're going to talk about that later. This track list is the current list of tracks there. You can also remove them from here. This is everything in display there. Finally, you can also upload local tracks, which means, so for building a custom track, the standard in the field now is you need to host your data on a server, right? Because it's a remote hub, for UCIC, for wherever, you save your data on a server. And then you use this browser, you point your browser towards that data. So you build your custom track is actually physically sit somewhere on a server, and then the browser goes in to access it. So that's the state of art, out there. But it does require you to have a server, which is not always feasible, right? So, upload local track is, you can upload stuff from your local computer, so just to make it, a little bit easier. The downside for this is it's difficult to host like a whole lot of data, right? So, for server, you can have a lot of data there, right? So that's the tracks. So we have now let's talk about we never talk about setting, but this is easy. But let's talk about apps. So there are different types of applications. So right now, so we're gonna demonstrate later gene set view, scatter plot, and things like that. But right now we're gonna do session, okay? So session, if you click session, you now have different options, right? So you can upload a saved session, which we'll do a little bit later. But now the point is, let's save our session. So this is the session ID, right? So the mechanism we use for this session is, we're gonna host this session ID, right? But you're gonna share this session ID because this is public, right? This is public, right? We don't want people to be able to guess that session ID. So only you will hold on to that session ID and then share with, whoever you trust. We do not have the bandwidth to do the security thing, right? So right now, this is the session ID. Is there a question?
Yes, from the TGent. They ask, can they export data in tracks from current visible region in browser as a table of value? If so, how to export those data and what would be the format?
That's a good question. We can fetch sequence. I think we can get the slice of data. I don't remember how to do that because the data, we access the data, so you can get the data as a table. The format is just whatever you see is whatever you get. So it's the table of numbers. That's what I remember. So you're not going to get, for example, if this part of the data is from a big week file, you're not going to get a big week file. You're going to get the numbers that get displayed. Okay, so it's probably not a very useful function, right? So the browser does not support, download of large data. So it's a visualization tool. Okay, but you can get numbers. So whatever is displayed, that number you can get. Okay, so that's my answer. Okay, so coming back to session, so you copy the session ID. You can save it somewhere, or right now I just copied it. And then the other thing is, in one session, you can actually save multiple instances. So what I'm doing here is, I'm going to give my instance a random name, Happy Lime Buffalo, whatever that means. I'm going to save it. So I actually have one instance of my session saved, okay? So I'll show you how, why this is useful. So now I'm coming back here, okay? So I have an interesting view. I saved it, okay? I'll continue working on my browser in the same session, okay? So, okay, this is cool. So I'm gonna now combine the tracks. I'm going to go to a different location. I'm gonna, I'm going to move this one. Let's see. I'm going to move one of them up, move this one down, like for example, right? So I did a bunch of other manipulation, or that's how you do research, right? You play around and then, whoa, I like this view even better. What you do, come back, you are still in the same session, okay? You generate another session, you save another one. So that's another instance. That's a time stamp, right? So you save that. So you can do this, you know, until you're bored, right? So you just save a lot of them, okay? And then you go do whatever you want, you know. But the record is there, right? So what you can do is share that ID with someone, or come back to that ID, you know, some other time. To demonstrate this, I think I can. What I'll do is I'll open a. Oops. So I've been using Google Chrome for this. I'm going to open a Firefox, okay? So I'm going to go back to my Epigenome browser, right? I'm doing the same thing as we did earlier, but now I'm pretending I'm a different person. I'm going to retrieve that session, okay? So I copied, did I copy that? I think I did, right? I copied it. I'm going to retrieve that session. Aha, I got my 2 timestamps there, right? So I can choose to restore any of them, okay? And check out what's going on in Firefox now, right? It's being restored. So this is, right? So this is all being restored. This is the first saved instance. Right? So this is something I hope, you know, pretty useful, right? So you work on your browser, you test different things, you save the sessions periodically with funny names, right? And then you can share this, recreate this easily. So so this function actually allowed us to create another function that's kind of fancy, but also spooky. That's something we call live browse. The idea is, if you can share this session live, can you share this session live? Which means I'm going to do my manipulation over here, but you can see it. You open on a browser, you can see it. Okay, now I'm in St. Louis, you're in Los Angeles. I'm working on a browser session that I shared with you. You can just sit back and look at all the things I'm doing on the browser. That's a new function that we created, we call live browse. I say it's a little bit spooky because, you know, you might find, okay, I'm sitting there, someone's working on that browser and moving tracks, right? So that can be interesting. It can be an interesting feeling. So let me just demonstrate this. Go live, okay? So I'm gonna go live. I click on that. This actually creates a new URL. I'm gonna copy that URL. I'm now coming back to this Firefox. Ooh, what's going on? Oh, okay, it's loading. So what happened here is, whatever I'm doing over here is going to be reflected over there. This is where I really hope the screen is much bigger. You know, I can put one over here and then the other over there, just so that you see, you know, what's happening, right? So let's give it a minute to load. So this is actually the same session. You know, we're looking at the same session between these 2 browsers, right? Okay, let me manipulate this. Let me, you know, I'm gonna remove, sorry. What did I do? I'm gonna remove this track. I'm gonna move this to the right. Whoops. Something's okay. So so I'm doing my operations over here. Wait, I think the live one is, so this one is sort of reflecting whatever I do over the other side. Okay, so that's the live function. Okay. Okay. Oh, sure. Yeah. Yep.
As live, but my collaborators could look at this, say, wait a minute, what about this track? What about this region? And that person could actually do something, and it's still live, shared by.
Yes.
Can you do that?
That's exactly what it
So
offers.
it's not one
No, it's
direction.
multi. So you can share the same session ID with 15 people, and you can all do the manipulation.
Oh, I see. So
Yeah.
it's a totally shared workspace.
Yes, it's all shared.
Okay,
it's
great.
all shared.
All
But when that happens, you know, it's really the time order of events that
Right.
happen on the, right? So, yeah.
Excellent. Thank you.
Can you repeat the question for the remote people?
Right. The question was, is go live just one direction? That is one presenter and a multiple kind of audience. The answer is actually you can't go both ways. So everybody participating in the live session could basically also on the fly do things to that particular session, and everybody else will see that, right?
That's correct.
Okay.
Yeah. Yeah. So this is actually a new function in this new version of a browser. It wasn't available in the old one. Okay. All right. So I think that's that. I'm going to I know. So continue on the session theme. Okay. Continue on the session theme. The other way of saving the session is you can actually download it. Okay. What does this do is you actually downloaded a JSON file, a file. This is the file. This is the file that actually defines your session. So for those who are sort of savvy with computer code, you'll see this is actually what's making everything happen, right? This file defined your session. Okay, and you can save that. And of course, if you save that, you can, where did I save it? Download, okay. You can restore. You can actually do, go to, we'll just start another instance here. But now when you restore your session, you can upload session, right? You can upload, I don't know, I think this one is it, right? I don't know. We're not gonna open it. Aha, so you got your sessions restored. You know, you restore and go back to, they're fetching, no, not this one. Not this one, it's a different one. It's the other one. I'm gonna upload, maybe it's this one. Yeah, this look more like it. So now, yeah, I'm restoring this session this way, right? So you have multiple ways of restoring the session. Okay, so now I'm going to demonstrate some some other functions. So this one, I'm going to first restore a session. So I have saved a session. I'll show you why I saved that session, and then sort of go from there. So the session, I'm going to now upload a session that I saved before today. This one, okay. I'm restoring a session. So this is actually related to some of my own research, right? So I work on transposable elements, right? So in fact, one of the reasons that we have an epigenome browser is because I want to see data on transposable element, and I want to be able to find them quickly. So I really needed a tool to do this. So this is the kind of data that actually got me excited. So I'm showing you 8 data tracks, right? So the top 4 are data from K562. This is ENCODE data. This is K562 is one of the ENCODE cell lines, right? And these 4 are also ENCODE data from GM12A78. So these are classic ENCODE cell lines. For each, I have 4 types of data. I have a meso-CRF. This is essentially methylation, right? So the ticks are CPGs, and the height is methylation level. This is not whole genome bisulfate data, but this is modeled to look like whole genome bisulfate data, right? So this is methylation. So you can see the genome is pretty heavily methylated, except at this region. The second track is actually a ChIP-seq on JUND, right? ChIP-seq JUND, right? Next one, I think, is K27 acetylation on JUND, right? Next one is K4 monomethylation on JUND. So basically, you can see, there's a transcription factor binding site, an enhancer probably because you have K4 monomethylation and K27 acetylation, and you have ChIP-seq, and this region is slowly methylated, right? So it's a classic enhancer. You look at the same experiment: methylation, ChIP-seq, K27 acetylation, K4 monomethylation, but on different cell line, GM lines, you see a different peak, right? So this is sort of, you have cell type specific enhancer here, right? So it's pretty classic stuff. So the part that most interesting to me is, where are these peaks? So let's just zoom in this a little bit, okay? Now you'll see this peak actually overlaps with a transposable element. This is the repeat masker track, right? For most people, I think most of the field thinks transposable elements are junk DNA, they're useless. But this one actually clearly argues that this transposable element is a bona fide enhancer, right? I'm showing you this differential peak to argue that this is not mapping bias. Mapping is problematic for transposable element, but when you have this type of data, is not mapping bias, right? So this is the kind of science that I'm mostly excited about, okay? So the next question would be, well, if I have one transposable element, which is, in this case, is called MLT1L, I believe, MLT1J, right? So this is the transposable element. Transposable elements are repetitive, right, across the genome. So there are many, many other copies. So my natural question is, does this only happen to this one element, or does it happen to other elements of the same family, right? Because sequence-wise, they're actually related. How do I pull my transposable elements together so that I can evaluate this, right? So this is, you know, again, if I have 100 candidate, I'm going to open up 100 windows to look at, you know, all my element, right? So that's sort of the classic way of doing things. But for my own research, I needed a way to now break the genome into pieces, and I'm only going to look at the part that are important for me. Okay, so this is where this is where I'm going to use this function called gene set view, right? Basically, you can enter a list of gene names, and you can have all the genes put together next to each other. You can also input just a set of genomic locations, and you'll be able to look at those locations right next to each other, right? So that's what I'm going to do. So I have my little cheat sheet. I'm going to go there. I think we lost that page, Epigenome Gateway. We're going to go to support. We're going to go to this workshop. This is my cheat sheet. This is my region. Okay. By the way, this is the session. So if you want to load that session, you can do that yourself. This is what the session looks like. Okay. So this is the quiz for today. You're going to remember this, right? Anyway, so this is the regions that I want to look at together. Okay, so we use this gene set view. Okay, I'm going to create a set. These are my regions I'm going to add. Okay, so now I have a set of regions, or I think I have 20 regions. I have a set of regions that I defined. Okay. So these are actually 20 transposable elements. Okay, just like the transposable element I showed you earlier, you know, that's one. So now I have 20. Okay, so I'm going to look at all 20 of them together. I'm not just looking at the transposable element itself. I want to have a little bit of context. So I want to add a few bases around this transposable element, right? So I'm going to say add 2000 base pair upstream, maybe 2000 base pair downstream. Okay. I'm going to give it the name. I'll just TE2KB. Okay. I'll just give them this name. Okay. Now I'm going to add the site. What did I do? Oh, no. Okay. I'm going to come back and fix this. I hopefully I saved this correctly. Okay. Now I'm going to enter gene set view. I think this is okay. All right. So we're seeing 20 regions next to each other now on the genome browser. Right. Now remember, we started by looking at one such location, right? And that location is, where's that location? Okay, so here's the different regions, right? These are the different regions. These are the different regions. I think maybe this is our first location, right? This is so the regions are separated by gray lines. Unfortunately, we don't have the resolution to see this, but these are 20 regions. Right? You know, the gray lines are separating the regions. I think this one is the region that we look the first, right? Demethylated in the middle with the ChIP-seq peak here for transcription factor gene D, K27 acylation, K4 monomethylation, right? So that's sort of centered on that transposable element. So the same region in the GM line, this peak is shifted on the side, right? But because we have that 2KB context, we can see this. So this is first example. Now we're looking at this 20, we'll see, there's actually more of such example. For example, here, this is actually two regions. There is a gray line right here, right? So see, this one has a Jun-D chip-seq peak, right? This one has a Jun-D chip-seq peak, right? So you see, this is not unique to that one transposable element. In fact, there are more. So these transposable elements are all from the same family. Some of them, you don't see anything, but some of them are indeed recapitulating that one, the pattern of that one, right? So this is not, this is important for our own research. Now we can look at multiple things together, right? And then, to know, what are the rules, what are the exceptions. So this is putting them right next to each other. You realize if you can do this, you can now do some pretty basic but useful bioinformatics. One thing you probably run into very often is if you have a bunch of regions, say you have your 200 promoters, I want to generate a profile, stacking up all the promoters together, I'm going to generate a profile, right? So, you can see promoter is slowly methylated with high K4 trimethylation, things like that. Now you almost, gonna need this immediately. You think, okay, what if I align all my transposable elements together, now not side by side, but I stack them together, and then let me, what the signal look like? What's that signal look like, right? So you can do that. You can do that by using this gene plot. Okay. So gene plot, by definition, is if you have a bunch of genes, I'm going to create a profile for your genes, basically create their epigenetic profile. Again, it's very commonly done when you look at demethylation. Promoter gene demethylation is low, gene body is high, right? So you can summarize this information across many, many genes. It's a very common bioinformatic task. So here, my gene, quote unquote, is actually my transposable element, right? So I want to stack them up together and create a profile. So my set is my TE2KB. I'm going to pick, say, this Jun-D as my data set. I'm going to plot, box plot. I'm going to generate a plot. I mean, you see this type of plot a lot in papers, right? So the center is transposable element, right? So this is sort of a genomic, this is 20 elements added together, right? So you can see there's actually a lot of outliers in terms of chip signal over these transposable element, right? So these are the things that people actually generate and publish, right? So, stack of binding site, stack of open chromatin, and you don't have to write any code. You can do it with this, with the tool here. In contrast, let's say you want to do a control. You can, what about my GM line, right? You plot the same. There's nothing, right? So you got figure 2A and 2B done now, right? You can also do, okay, what about demethylation? This thing, this isn't quite right. Let's see. No. Yeah, this graph isn't what I expected. It's a little bit lower than I expected. Anyway, so that's one thing that you can do. There are a few such functions like this. A related function is to create a scatter plot. So now you say, okay, I'm going to still use my set. I'm going to look at correlation between chip-seq and K27 acetylation. What's the relationship? You sort of see, a generally sort of a, this is sort of, basically the scatter plot going, you have sort of a positive correlation between these two signals. Okay. So again, the mechanism is simple. The idea is now you can slice and dice your genome, and you can dice and dice your data, and now you can perform some bioinformatics with this type of data. Okay. So we're now going to exit GeneSet view. So GeneSet view is a fairly useful tool for us. Okay. Okay. So I think I've done the GeneSet view. I've done the session go live screenshot. Screenshot is, so I guess this fetch sequence is to get the genomic sequences. Screenshot is fairly useful. Like, you create a browser shot, right? So you can download a very high resolution, map, right? This is create a SVG file, and then you can create a PDF from that, right? So this is, again, a very useful function, creating high resolution screenshot. You don't have to do this, capture the screen, right? You can actually generate the SVGs. So that's that function. So next, I will show you how to look at Hi-C data. Okay, I think I covered. I might be missing certain things, but we've done the go live. Okay, let's now do the Hi-C part. Okay, so what I'll do now is I think I can. I'm gonna remove these tracks. Okay, I'm going to go to the track table, public data hub. I'm going to import some Hi-C data. So the specific data set I'm going to import now is Hi-C interaction from JuiceBox. I'm here, we collaborated with lots of people. So in this case, we actually use JuiceBox as an engine for fetching data. So they actually developed some nice software that allow us to access the data. So we now just added 192 Hi-C data. So this, actually right below this is a FASTA table that you can already choose data from. So what I'll choose, one of the GM data sets. So these are all the GM data sets. I'm going to add the first one, right? Just to okay. So this is sort of by default, you see some chromatin interaction data already. These Hi-C squares. It doesn't look nice yet, right? So we're going to show you how do you configure this track to actually generate the kind of figures you see from publications. Just to make this more interesting, we're going to also import some ChIA-pad data. I'm going. This is part of getting old. So the track I want to show is here. So let's import this hub called long-range chromatin interaction. Okay. I'm going back down and find my GM. So I think we actually are getting chip. Let me do this filter. So this is actually good because so we got a filter chipad data, right? So let's load this track. So this is again, we're sort of recreating what we went through. How do you find data, right? So I'm going to add this chipad data using CTCF on the GM line. Okay. I think there's one more data set I want to add just to make the point. I am going to add another. Where's the, I need to increase the chipad height first. Okay, chipad data is getting the height it deserved. Okay, I'm zooming out a little bit just to, that allows us to see a little bit more. Okay, so I'm going to change that into ARC mode, right? So chipad, I changed chipad data into this ARC mode. I'm going to zoom out a little bit more just to see the pattern. Okay, so that's sort of what the chipad typically, displayed as. So by default, you can see the resolution of the high-C map is changing as you zoom in and zoom out, and you can force that to be a specific, at a resolution that you like. So we're going to use these options. Okay, this is where I need my cheat sheet. We're not gonna do normalization. These are the classic ways of doing normalization. We're gonna stay at the heat map, but we're gonna keep the height, but I'll change the score system, okay? So I'm gonna change the score system. So now it's like the score max is too low, so everything sort of light up. I'm gonna use 5,000, okay? And I'm going to change the bin size to, so this is automatic, right? These are different resolutions. I'm changing that to 25 KB, right? So this means we're fetching a little bit more data, but it's going to generate a prettier view for you, right? So this is actually, more similar to the kind of high-C map you see in publications. You can sort of see this interaction, this domain is recapitulated by this, right? This interaction is recapitulated by this, right? So this is, comparing high-C and chipad. So this domain boundary, has this CTCF link, right? So we can make the CTCF data look a little bit stronger, so make it 6, right? To compare this. So the one last track I want to add to make this view is, I'm going back to the hub. So we're going to load yet another hub that is called Encode the Legacy Hub with 4,000 data sets. Okay, loading. Okay, loaded, 4,000 data set loaded. So now I'm going to search for CTCF ChIP-seq. Wait. In GM. So we see a few. I'm going to add one from John Stam's lab. I think I know there's another CTCF ChIP-seq from someone else for maybe, yeah, let me see. So this is the CTCF's track. Let's make it taller. Right. So you can sort of see now all these 3 data sets sort of coming together. This is a big anchor point separating big domains enriched for CTCF site. Right. 3 different experiments from 3 different labs, sort of giving you the same story. Okay. So this is how you look at high-C data. High-C data is kind of sometimes it's an art for you to find the right view. Use the right normalization, right resolution, and density contrast. But because we have a whole lot of other data that can be used to decorate and support this evidence. So the beauty of this browser at this point, you probably see, is you can just continue add, right? You can just continue add on top. Now probably the most popular way of looking at high-C data is JuiceBox, which is a great tool. But JuiceBox is really you look at one high-C data at a time, right? If you want to add some other decorating data like CTCF binding site, you add 1 or 2 and that was it, right? It's difficult to look at multiple multiple high-C data sets. But here you don't have a limitation. You can look at high-C, you can look at ChIP-pad. You take your high-C, you can turn that into an arc view, right? So this is how you actually turn high-C into an arc view. And then same thing, you can turn ChIP-pad into a heat map view, right? So you can do a lot of this type of manipulations, right? So that's looking at high-C data. I think I do have another function I was going to show, but kind of forgot. So we're coming back to this view. I'm glad I haven't closed it. So this function is, so there's a way, so you still look at one track at a time with this, right? So we have a way of combining tracks, right? So for example, if you want to combine these 2 tracks, because sometimes you want to look at the contrast, you can apply something called matplot. See, this is, I think I clicked it twice. So you generate a new plot, new track, right? That is really a combination. You basically put these two tracks together that way, right? So sometimes it can be a convenient function when you want to see just how closely related are these two sets of signals. Maybe they superimpose each other or they're completely different. So that's a function that we provide. It's called matplot. I don't even remember why we called it. So let's try one more thing. So this might break but this is this is where we want to do more development. That is the 3D version, right? So we're 4:30. We're getting tired, but I'll just show this one, and then we'll call it a day. Or I'm happy to answer questions, of course. I'm going to show try this one. So click on the 3D thing. This one doesn't work, that well yet. We're at the very beginning of implementing or developing this function. Takes a little while. So at this point, it's very simple, right? It's really letting your track stand up, right? And then you can, I can't even manipulate it, I guess, very smoothly, right? And you can actually put on this VR goggle and then really work on this. How do I turn? Come on. Work with me. All right, yes. Right? Yeah, so that's the arc. So it's very simple at this point, but this is sort of the direction I think we want to go. Right now, the genome is not binding yet. It's a flat space, but hopefully we're going to allow it to wind and bind, right? And you can jump between different parts. Your data will show up as sceneries as you walk along the epigenome roadmap, right? Yes. I'm sorry. For the current view, you're looking at two. Right. So I'm sorry. I should explain the data type. So the pink arc are high C data. Okay. So this is high C with certain cutoff. There's parameters you can turn. So that's a loop defined by high C. Right. So these two parts of the genome have a high C interaction. The blue tracks are chip-seq. I think I actually don't know which. We have a chip. Yeah. So this is the CTCF chip-seq, right? So that's the two data sets that we are looking at. So you can see this chip-seq signal is actually right at the loop boundary there. Like this is a domain, right? So you have a big loop here or domain boundary. This is your CTCF binding profile. So this is essentially this over here, right? So this is the CTCF binding, and that's probably, I think this is the big arc that we're seeing. So again, this is the data. Right? So what we're seeing there is that big arc with that bunch of CTCF side there. Okay. I think at this point, if you want to move this, you can, let me try to move this, and then you got that redrawn. Yeah. You got that redrawn. This one is still, computationally more intensive than I want. So we're continue working on this. But hopefully you'll see, we're having lots of fun. Right? We're working hard to make this more useful, but at the same time, we really enjoy doing this. This is lots of fun. Okay. I might have skipped this stuff, but I think this is pretty much everything I've prepared. I'm happy to, answer questions, or if you have specific requests, which part of the browser that you want to see more, let me yeah, so it's just, the floor is open. Let me think, what else do I have here? There are other parts that, like for example, other things like change this and that. So there are lots of other bells and whistles that I did not show. But if anything, if you sort of found this interesting, I encourage you to just spend some time. Spend some time on the browser, get familiar, ask questions, Slack us, right? Yeah.
Any questions?
I have one.
Yes.
So, Ting, is it possible to display human and mouse same region in the same view?
Yes. Okay, I didn't prepare that, but let me see. This is a special track type. Where is that? That's how do I get there? I don't remember how to get there, but yes, we have that function.
I remember we used it, but I can't think. I think that would be helpful for the audience, but I can't remember either.
Yeah, we do have that function. Well, we never published that function, but people actually published papers using that function. That's pretty, pretty nice. So so that function is not fully developed, which means there are lots of features that we want to have. We haven't developed them, which is why we haven't published. We have the basic bare bone ready.
That reminds one of the questions said, do you have an FAQ, like archive, whatever question I have to ask, that you have an answer? Do you have an archiving system for people to search that? Can you show that? Maybe?
That's right. So we have, so here's where, so the previous years, we've been mainly using this Google Plus forum. Right? So people ask questions there, everything's archived. I think Google closed it. So we are switching over to Google Groups. But we have everything that we had on the Google Plus forum archived. So, you can search for old questions. More recent thing is this Slack, right? So you can just Slack us with your questions. So we also document everything, save everything on the ask on the Slack. Yeah. Yeah, the comparative track. Where is it?
Comparative.
I don't even remember. I didn't prepare this part, so I didn't.
Can you Slack it now?
Yeah,
Asking your group that could show us your group is responding to questions.
Sure.
It's probably after hour.
Where is our comparative track?
That is the favorite guys that you should remember.
Genome alignment. Oh, we call that genome alignment track. Yeah. Yeah, well, this is, they're 6:30. They're probably just left. Yeah. But it's called, I think I can find it on the old browser. You know what? Yeah. Legacy browser. Go to the browser. HG19. This is our old browser. We continue to support this for at least 2 years. That's the, we could just go to the genome browser. Tracks. App. There's a genome alignment. Genome align, yeah. Okay. So we can choose MM10, submit. Voila, there you go. You got your human and the mouse aligned, and then you can add your genomic data. So that's, let me add some data.
Can you just repeat it?
Oh, sure. Okay.
I'm not sure if
So
everybody.
what I did is, this is the old browser, okay? So it's the comparative genomics browser is essentially one track type that we call genome alignment track. So to get there, you go to app, right? The name of this app is called Genome Align Track, right? So I click on this, I choose MM9, because my home base here is HG19, right? I have existing alignment from HG19 to MM10, so I choose MM10. That's what I clicked. I submit, and this is sort of the track type, right? So this is the genome alignment track between human and mouse. Okay, now you can upload your genomic data and you can look at human data, mouse data in the context of syntactic alignment. So this represents the alignment, right? So this is the, compare, aligning human and the mouse. You can zoom in and then all the way to base pair level alignment, right? And interestingly, I can't find it on new browser at this point. Yeah. You can zoom in to really see the base pair level alignment.
So this is the alignment. Is it possible to generate the view showing the epigenome?
So that's, yes, so you upload data, right? So let's give it a try. Let's see. I'm going to now go to public data hub. I'm going to load our epigenome data. So there you go. You got human data loaded. How do I load mouse data? I don't remember how do I load mouse data, but this is the idea. So human data loaded, and you have alignment.
Can you hear us here from here, the Monrovia building?
Yes, we can hear you.
I think in the new browser, I'm not sure, but is it under the annotation track?
Ooh, let's go there. And then, thank you. You should run the workshop.
I'm not sure, but I just want to double check with you on the.
Yeah, sure. I mean,
Then you click on HG19. There's a genome comparison.
Yes. Yes.
Okay.
Oh,
I'm
thank you, Yang Lu. That's a good one.
Yeah, this is Lu Yang.
Lu Yang,
Yes. Thank you.
Great. So we are on the same.
Yeah, excellent. Yeah, we're adding
excellent
the.
job.
Yeah, I mean, I don't. There you go. Yeah. Yeah, I mean, the browser is like pretty substantial at this point. I use the browser every day, but I don't use all the functions every day. I don't sometimes not. This I I don't even remember this part. Yeah, but thank you. I still don't remember how to add mouse data. Let me see if the Slack. Nope, no response on Slack. But it's 6:45 in St. Louis. It's dinner time, picking up kids, that sort of things.
Okay. Any more questions? Lu Yang from the other side. I checked TGN. They don't have it. How about you guys in Monrovia?
Okay. We're good. Thank you.
Okay, got it. All right, so that's all. Thanks, Dr. Ting Wang, for a fantastic, prestige genetics. Not only generate data and trying to make the data available for us, and then you can actually visualize and better annotate using your own questions or even upload your own data set. So that's give the round of applause for him.
Thank you very much. Thank you.